Good afternoon, everyone. My name is Stephen Mellor, and I'm guessing I don't need too much of an introduction. I'm here today to talk to you about architecture, not specifically in the way in which Mellor thinks about it, namely a completely domain-independent architecture, but rather some of the principles that go into making an architecture elegant. So if you'll give me a moment, please, I'll find the presentation and we're off to the races. Everything has to be somewhere. Okay, now I'll make myself a little bigger. Okay, and we're off. So, elegant architectures. What brought us here? Well, first of all, Court asked me if I wouldn't mind having a chat. That green square was intended to be the same size as the picture, but since I had to move my computer to a different computer because of lighting problems, it isn't quite right. But never mind, we'll survive. So when Court first came to me, the original request was to talk about Mellor in the Industrial Internet of Things. You might know that I currently work for the Industrial Internet Consortium as its CTO. I am IIC is a program of the Object Management Group, which is, you also undoubtedly know, the people responsible for UML and the action language and all the other work. So what I'm doing right now is focusing on the industrial Internet of Things. What that means is connecting things like factories, chemical plants, cars, hospitals, etc., to the internet so that you can gather data across multiple instances and therefore make better decisions. Consider, for example, a factory or even a set of factories that have identical production lines, and yet this particular machine over here, this particular production line is kind of slow and it breaks down a lot. Why? Well, if you can compare it to others, you might be able to get things done. But unfortunately, in terms of Mellor in that particular side of the world, this page says it all. I don't see Mellor at all. I don't see people talking about it. I see people thinking in terms rather at a higher level, in terms of the kinds of functions that we need to be able to execute. But I'll come back to that towards the very end of the program. Then Michael Lee, who again everybody knows from Model Integration, asked me about architecture experts. He, I believe, is doing some work in respect to the history of Mellor and who's good at architecture and so on and so forth. And when he asked me that question, I thought of one immediately. That person is named Diomedes Venelis. He works at the Athens Business University. That's not the exact title, but that's roughly the kind of area that he's working in. And he has a book in conjunction with another fellow who I have not met called Beautiful Architecture. It's a compilation of different ideas, different architectures, and how it is that you might think about them. He asked me to write a foreword. We met on the IEEE Software Editorial Advisory Board. And what I did was to read it over and then try to abstract some things that I thought were universal principles that we might be able to apply. Now, this book was published in 2009. It's quite old, but nevertheless, I think that the principles are timeless. So the first thing that I think is a characteristic of a good architecture is one fact in one place. What does that mean? What is one fact exactly? Well, first of all, it needs to be non-decomposable or atomic. It needs to be independent of everything else. And you are, of course, Mellor practitioners, and you know right away that one way of thinking about this is normalization. Break it down to the individual components, ensure that each component is independent of the others, and go from there. And of course, you've all seen the classic example, dog owner. But this idea of one fact in one place also applies to behavior. And if you listen to the agile folk, they'll talk about factoring and refactoring. If you go back, way back to structured design by Myler Page Jones, with whom I went to college, you'll see a discussion there about breaking things down so that a single function does a single thing. It's the same idea. So when we talk about a fact, we're not really just limiting it to data. although the notion of normalization in data is well formalized, whereas the notion of factoring in behavior is not at all well formalized, to say the very least. So that's what we mean by one fact. And it's no surprise that a certain company with whom you are all familiar is called that, because this truly is a fundamental principle of an elegant architecture. What do we mean by one place? Well, any practical software engineer knows right away that you can't always just have one piece of data in one place. You can't put everything in the data center and then run up there to get the information and then back down to the actuator and cause the control to happen. That won't work. Instead, the way to think about it is to think about it in terms of one place to modify. Now, before I go on to the ellipsis at the bottom here, I'd just like to mention something that is becoming more and more important and popular, namely distributed computing in the edge. I did mention the data center just now, and the data center has certain capabilities such as virtualization, multi-tenancy, and so on and so forth that allow you, in principle and in the simplest way, I think, to be able to put one user's information and data on one machine, or to spread it across multiple, and indeed you could share it with many other organizations, many other people. So the idea then is that you can then scale up and scale down, scale in, scale out. You can very quickly build up something using what we've commonly called the cloud. I think actually that as the understanding of this has grown, that we need to separate the logical from the physical, another thing that I'm sure you've heard before, and refer to the data center as having cloud capabilities. But you can also put cloud capabilities, quotes, in the edge. And what we mean by that is closer to the sensors and closer to the actuators, and in fact anywhere. For example, in a smart city, you might have some information in a building with a bunch of servers, which is then put together into a district and then into a city, and so it goes. So what we have then is the idea of distributing computing between the data center and the devices, whatever they may be. In addition to that idea, we then have a notion called data gravity, which is where the data and the computation come close to each other. They draw each other together, because you want to be able to compute on data without sending it off miles over there first, so that it can come back and then you can do something with it. So what that means then is that computing is distributed between the sensors and the actuators and the data center. But back to this idea. Only one place to modify. What does that mean? Well, what it means is that if a fact has to be duplicated, that is to say, in more than one place, then that propagation needs to be automatic and not manual. It's simply too expensive. Moreover, it is simply far, far, far too error-prone. You can't do it. Now, at runtime, what that usually means is specific kinds of architectures, including proxies and broadcast mechanisms and all that kind of stuff. There are multiple ways of doing this, of course, as you know. Duplication of data, automatic periodic update, update on request. There's many, many ways of doing it. But the underlying principle is that it has to be automatic. Now, at construction time, it has to be built in. And what that means is understanding that there is one source of truth, and especially for data. Those of you that attended some of the project technology courses will remember a biomedical treatment facility. The key thing there was to keep all the data that described everything in one place, and then to generate where the data needed to go, to generate how it is that you wanted to manipulate that data. This is very important. Here's another example. Sally Schleyer and I worked on the Bay Area Rapid Transit System for a while, trying to replace this control system. One of the things that they were doing was building additional track. Now, what that means is that you're going to have to get that data in so that you know where the track is and how you can describe it. So how are you going to do that? Well, that unfortunately is likely to be a manual process, but it has to be defined in such a way that the minimum amount of data needs to be entered, that it is easy to test, to validate that it's correct, such as, for example, transitive closure to ensure that you don't have a piece of track that's completely separated from another piece of track, and so on and so forth. And then, should that data be required in different places, it's all propagated from one place automatically. And here's an example. Systems change. To avoid entropy, they need to be generated. And this is the example I was just using. This piece of track was about to be new. At the time that we were working on it, it essentially had 3 legs. If you know the area, I didn't go out to Dublin, Pleasanton, Livermore, over to the bottom right, nor indeed up to Pittsburgh at the top right. So that means again that you have to generate things. Now the key point here is less about generation than the fact that if it is not generated, it is easy for the system to deteriorate. And when systems deteriorate, they are not at all elegant. They turn into maintenance nightmares. You really don't want that. So this idea then of being able to generate is really a whole field. Generative Programming is a title that I've seen quite recently. There's a book here from Krzysztof Sarnecki, University of Waterloo, with whom I've spoken a number of times. And there are all sorts of different ways of making this kind of thing happen and making it easier. And they work at different levels of abstraction across the entire architecture and the construction of the architecture. One approach is to define a domain-specific language so that you can talk in the language that is of interest to the particular domain, hence the name, obviously. With a domain-specific language, then, you can write your, quote, program in terms of what it is that is being done in this domain, and then generate further code from that, going down across layers of abstraction. This is really a very old idea. For a long time, people talked about automatic programming. And the first use of that term was actually with Fortran, because it automatically figured out which register to put your variables in and how to organize your memory. All that's going on, and we've seen this multiple times in Stephen Mellor and its history, is we're raising the level of abstraction. So metaprogramming is another way of thinking about this. This is a way of saying, write a program that writes the program. And there's multiple ways in which this can be used, and it is key, I think, again, to maintain a clear separation between the different domains. Classic example here, and again, I'm going to go back to programming languages. If you think about a domain that is concerned with managing sensors and actuators, it might read a number, and that's all it is. It's a real number, and I do something with it. I convert it into something. Ooh, look, that's a temperature. But then when you go to the domain of the application, you don't think of it as just another real. You think of it as a data type called temperature. So this is another way in which you can get these things going. Here's the third way. Aspect orientation. This got very popular for a short time and then kind of disappeared. But the underlying notion here is you can bring things together. And another example of that area is something called multiple dispatch. I was reading actually just the other day at the local hostelry a story about a programming language called Julia, which is used a lot in mathematics and physics. And the way in which it works, and there's an excellent analogy, I thought, in a publication called Ars Technica. I don't recall the author, unfortunately, sorry. But the way in which we organize things by function is things like boil, bake, broil, fry. But the way in which we organize things, if we're thinking in an object-oriented manner, is chicken, fish, steak. And then we apply these different approaches, fry, bake, broil, etc., etc. And so when you think of things that way, and I'm just stealing this analogy directly from the author of this particular example, what you have to do then in the object-oriented way is that if you add a new kind of thing, you have to change it. right? If you in the function-oriented way, you have to think in terms of what the objects are, what the things are, I shouldn't say objects, what the things are on which you're operating. So neither of them is exactly perfect. But if you could just say boil chicken, well, I wouldn't want to do that. Let's say bake chicken, and get multiple dispatch so that we can look at things in two different ways. That actually is another way of thinking about the kind of stuff that was going on with aspect orientation. And of course, another approach is archetypes. And if you're interested in examining different ways in which we can generate programs, I do recommend this work. This, of course, is the classic cookie cutter. What we want is minimal mechanisms that fit together closely. These rather strange looking dragonish creatures with the best cookie cutter I could find. But I think you understand overall the underlying principle. You don't want everyone to be writing different things and then trying to fit them together. I did see many years ago, this was also from someone on the IEEE software editorial board, write something called the Fractal fencing frenzy. And it ran something like this. You have a large field and a bunch of cows. Now what you want to do is to fence them in. So what do? Well, the field is large, you've got a lot to do. So what you do is you hire 1,000 programmers or fence builders, and you get them busily working away, building a fence here and a fence there and a fence somewhere else. And then you see how they fit. Well, guess what happens? They don't fit at all. One person is using barbed wire, another person is using Star Wars-like laser equipment from a satellite in space to zap the cows that try to go over the boundary. Some are using metal, some are using wood, some are 6 feet high, some are 5 feet high. You can't fit them together. So what happens then is that it becomes fractal. Then you have to build fences to connect all the different types of fences. And this just gets worse and worse and worse. So the better way to do this, of course, is to identify a minimal set of mechanisms, understand exactly how they fit, and then apply them uniformly, or as near uniformly as you can. Here's another, I think, elegant feature of an elegant architecture. It is reflective. This example is a little bit silly, but I'm using the dog owner. Actually, the first time we did this was for an aluminium or aluminum, whichever you prefer, rolling mill on which Michael Lee was actually working at the same time. And what we did was set up a bunch of tables and columns in memory so that they could be accessed quickly. And then we had a separate pair of tables, the table of tables, which contains the names of the tables, dog and dog owner, and then a table of columns with the name, which of course is associated with the dog owner, and the address similarly associated with the dog owner, dog name and breed with dog. Now, by organizing things in this way, what you're able to do then is to use the same idea to access a table as you can use it to access the table of tables. So you can minimize the total amount of stuff that you need to do. This, of course, needs to end somewhere. You had to know the first address of the table of tables so that you could find everything else. But with that, you can then duplicate this approach. You can reflect this approach throughout the system. And then we have a common idea that I think turns up quite frequently, again in different guises, building engines, virtual machines, or layers. The underlying idea here is to program in data. You can see that reflected in the notion of DSLs, where people are thinking in terms of the elements that make up the domain and how you can put them together, so that you can then change the data to change the behavior. Now, this is, I think, very important, because what it leads to is the fact that you don't need to program as much. And that's a good thing, because understanding how data fits together, how the components of the data fit together, is much easier to do automatically than to verify that the code is working. Let me go back to the example of the rail network and how the tracks all fit together. Well, if you can say, this track starts here and ends there, this one starts here and ends connected to that one, this one starts here connected to the one before, then you can write that down and you can test that very simply. You can very quickly then write simple testing programs that check that there aren't any gaps, transitive closure. So this is a key way in which you can make things happen. And the key thing, of course, in that is that the person who is entering that data is more likely to be skilled in understanding what that data means. So a way to do this is to use domains, of course, to separate out the different layers. It leads into different layers at runtime, and this, I think, is one area where we have failed pretty significantly in getting across the notion of domains very clearly. People think more in terms of the runtime than they think in terms of the underlying subject matter. And then data-driven engines. So the idea here, and I've used the phrase data-driven a lot, those of you that were ever in contact with one of our instructors named Wayne Hiwari, he went to Salesforce. Salesforce is a very, very data-driven program. I use it all the time, and it is very easy to manipulate, to add new ideas, to add new pieces of information, and then bring them together so that you can get the information that you need where you need it without having to do a lot of programming. Yes, you do have to do some on occasion, but by and large, because it's data-driven with a bunch of features that you can execute, then it's fairly easy to see how things go. Let me give you another example of this. This was a telecommunications company that was trying to automate calls coming in into a system so that you could direct the call to the right place. So think, for example, if you're calling up a hotel or an airline, not that many of us are doing much of that these days, unfortunately, and you'll get things like, are you traveling internationally or are you traveling domestic? Are you using awards or are you using something else? And you can just go through these steps. What you actually have is a decision tree. And so you can abstract out the decision tree and then write the program that traverses the decision tree. And then it's very easy to say, oh, well, you want to talk to this person who is on the east coast of the US because it's very early on the west, and it needs to be in the group of people that are focused on international travel. Simple enough idea. And then it's easy again then if you wish to add a new kind of function, someone who can answer a question about a particular kind of hotel reservation, let's say. You don't change the decision tree. You only change the functions that you actually construct. So data-driven engines is just a particular pattern that conform to these principles, it seems to me. These are all heavily interrelated. You can see, for example, going from one fact in one place to automatic propagation, going to construction being in the architecture, going to the different approaches that we've looked at so far. You can see that they all connect in one way or another. However, I must say, and I'm depressed about this, that domain engineering is still not in the forefront of development. I went back to Sarnicki's book as I was preparing this, just having a look at the table of contents to remind myself of some of the terms that he used. And one thing that struck me right away was domain engineering. Because if you're going to do something like a domain-specific language, guess what you have to understand? Let me think about that for a minute. Yes, that's right, a domain. So for some reason, although DSLs were popular for quite a while, the notion of a domain and being completely abstract simply has not caught on. If you take another look, for example, at some of the work that's going on in the object management group about, I'd say 15 years ago, a big thing was something called model-driven architecture. And they constructed things like a platform-independent model and a platform-specific model. What the platform-specific model did was to mix up both of the abstract concepts behind what the architecture is and the elements from the application, just the same as the kind of stuff that you see in elaborative development in UML. Big mistake. But if you can't make it understood, well, you can't make it understood. So you just have to move right along. Next thing to think about here, and this is important, is the order of growth. Those of you that took programming language classes, these many years ago, will remember tones, literally tones, from Donald Knuth on things like the order of an algorithm. So for example, what is the order of a linear sort versus a bubble sort versus a quick sort, or et cetera, et cetera. They tend to grow as the size of the system grows, and some of them grow linearly, and some of them grow exponentially, and some of them grow this way and that way and the other way. I did run into a system once that had a very small number of items that it needed to track. It was a dozen. I mean, it was nothing at all. So what it did was that it polled each one of the sensors and just asked, you know, what are you doing? What's your temperature? What's your pressure? What's your this? What's your that? And it carried on doing that, and it worked out until we had 24 sensors, and then 200, and then you can see where this goes. It doesn't work. You have to go back to an interrupt. When Sally and I were working on the Bay Area Rapid Transit System, we ended up writing a short paper called Where Have All the Cycles Gone? Because the architecture that was being proposed was highly centralized. And then we were trying to understand what exactly would happen as the number of trains increased. Here's the example. 1 mile of track, not trucks, has 30 blocks. These blocks essentially simply indicate that there's a train there. So you get an event when the train enters the block and also when it leaves, right? So 1 mile of track has 30 blocks, and then the train goes in there and out there, generating 2 events per block. So if you're traveling 1 mile is 60 events, because that's 30 times 2. Then at 60 miles an hour, that's 60 times 60, that's 3,600 events an hour, 1 a second. Now you multiply that by 100 trains and 100 miles of track, and how are you going to do that? So that kind of analysis, understanding how your architecture will change as the elements change, as the number of elements change. What happens when you add more sensors? What happens when you increase the cycle time? What happens if you reduce the response time that's required? And so it goes. Trying to understand each one of those different things will help you understand what your architecture should look like. And doing that properly, of course, is an elegant approach. You need to resist entropy. I first heard of the law of system entropy from Sally, which simply states that the systems deteriorate over time. Whether she invented it or not, I don't know. But what's pretty clear is that you need to make it easy to do the paperwork. That means minimizing the amount of things that you need to do to make a change. That means making it easy to find stuff. It means building engines. It means building constructive systems such that you take the data and generate the necessary elements, and so on. Let me give you an example of this. Just again, this comes from Bay Area Rapid Transit System. The original structure for managing the electrical network was written in Fortran and assembly code. Try to picture this. You have a track, a piece of track with a third rail. It is powered so that the train can move. Now there's an earthquake or something, or the train breaks down. What you need to do is to take the power off that third rail. So if you imagine a breaker to the left and a breaker to the right, what do you need to do? Well, you need to open both of those breakers, and then the rail is isolated. Hooray! Now, clearly, if for some reason you can't open the breaker on the left, then you need to look at all of the breakers to which that breaker is connected. So if the other side away from the rail is powered by 2 wires, each of which has a breaker, you have to isolate both of those. And you have to keep on doing that until you can guarantee that the rail is isolated. The original implementation was 70,000 lines of code, mostly in Fortran, but then it would jump into assembly code, parts of the other breakers, because they're all interconnected. And so people would find certain bits of commonality, and then they would just write that little bit of code and then jump around all over the place. It was a complete mess. It was error prone. Nobody, as far as I know, was ever hurt. But nevertheless, you can't get that right. You just can't ever. So what we did was we reconstructed it in such a way that we had a complete description of the electrical network. We wrote 50, count them, 50, not 70,000, 50 lines of code. And then those 50 lines of code would simply recurse through the network, looking for the things that were connected to other things. And then if that failed to open, mark it as failed, and then move on and keep going and going and going until you had success. Now, recursive functions can be slow. So what can you do? Now, we never actually implemented this because we didn't complete that project. But what we did then was that we generated code that actually contained all of the things that needed to be done in a uniform way, so that you could say, this was generated from that data. I know that's correct, or if I know the data is correct, of course. And then I can deploy that function with these essentially hard-coded breaker names and get the stuff done and get it done quickly. Again, this all goes together. Make it data-driven, make it constructive, propagate data, make sure that you don't have multiple things in one place, that is done mechanically. For that, of course, you need to have specifications for data entry. I've mentioned that before. A little bit earlier when I was thinking about extending the track, using that example again. And then the Agile folk have an interesting idea of the metaphor. I'm sure everyone on the planet at this point has been to Amazon at some point, or other internet shopping locations wherein we find the shopping cart. Well, of course, there is no physical shopping cart, but you know what they mean and you know what it means right away. So what that means is that if a programmer wishes to change something and they're working on how they might do it, then what they'll be thinking of is, well, how does this relate to this underlying idea of the shopping cart? How do we want to think about that? So this is another way in which you can do it. And then to become a beautiful architect, you need to understand there is no one true way. I have in the back bedroom here a large box containing some of the important to me papers that we wrote at different times. As you can see here, it's a little bit hard to read because it's rather small. This is a concept map for the design course, recursive design course. It is around 40 pages or so. And one of the sections in here is to understand how your architecture is built. And that means looking at the kind of system, the external process that you're trying to control. Is it event-driven? Is it continuous? Does it have a lot of data? Does it have just a few? Et cetera, et cetera. And then we classified, or Sally classified in this case, the different kinds of problem types that you could see. This is actually fairly exciting because now in the work that I'm doing, if you go to hub.iiconsortium.org, you will find a so-called Project Explorer that allows you to do exactly this, to go through each of the steps to identify how you can characterize your system and then use that information in multiple different ways, primarily to understand it and to come to a common understanding. But the key thing here is that these ideas actually, like domain engineering, at least are appearing in some places. So that's good news. But the key thing about this is to understand that if you worked on a telecom system last time and you were trying to apply it to process control, you're unlikely to succeed. Right? There is no one true way. You can't build a single platform. You can't build a single architecture. You have to understand that there are multiple things that you can, multiple ways in which you can build systems. Of course, another way to become a beautiful architect is to exercise more and eat less. I should take my own advice. So where are we? Architecture today. Technically, a lot has changed, particularly in terms of assembly from components. While we don't have domains as a concept, we do have lots of packages that we can bring together to build a system, so-called mashups. In Industrial Internet of Things, which is where I began, you'll recall, in particular, trustworthiness is much more of a concern. For those of you not in the US, or those of you who don't get to see Stephen Colbert, he prefers to talk about truthiness, and I like that term too. But the key thing here is trustworthiness needs to be designed in. You need to have cybersecurity. You need to have, in the industrial context, physical security. You need to have privacy and resilience. Most of all, in these kinds of systems, you need to have safety. And you need to understand that where the information technology world and the operational technology world come together, there are different languages. If I say security to an IT guy, they think, firewalls. If I say it to somebody on the factory floor, they think barbed wire armed guards. It's not the same idea. It's different languages, different emphasis. The IT person will think in terms of, again, firewalls, being able to secure the information technology. And so it goes. So what we need to be able to do here is to bring these two things together, and it has to be designed in. And that, I think, is a key element that we need to be thinking about as we go towards the future, thinking about architecture. And of course, technology and trustworthiness always need to support the business goals. I haven't written a program, apart, of course, from a kind of meta program, like in Excel, for example, for many a decade now. The focus for me personally is much more in terms of how it is that we meet the needs of the business and how it is that we can bring these things together so that we can do what it is that needs to get done. And the ideas that I use in that come a lot from the things that I learned in the time that we worked together and in the time that we thought about architecture. So thank you very much. I shall stay on the line now and I will take any questions that you have. Thank you all very much for your attention today, and I hope if you're in Portsmouth, you enjoy that. And if you are virtual, that you are remaining safe. Well, actually, I hope everyone remains safe, but nevertheless, let's move on from here. Thank you all very much. Good day.